Good morning, good afternoon, good evening, whenever you're watching this video. I hope you're doing great. Today what we're going to be talking about is what's called geometric probability. Now I know you all know what probability is. It's the possibility that an event will occur. But as far as geometric probability, it's a little bit more, you can kind of grasp it easier if you ask me, okay? Sometimes when you hear about probabilities, you're like, how did they come up with that? But when you talk geometric probability, you can actually visually see what's occurring. And we're going to try to make every probability that we look at today something that we can physically see and measure, whether it's a length or an area. And so that's the key concept here today. Make sure you can physically see what's happening, whether it's a length or an area that you're measuring. So let's just write down real quickly a generic definition for probability. And so it's going to be the number of favorable outcomes over the number of possible outcomes. So number of favorable outcomes over the number of possible outcomes. Okay, so if you've ever considered the two types of probability that you usually talk about in school, which are theoretical, things in theory that should occur, okay, versus experimental, where you actually put them into practice. This would be considered a form of theoretical probability. I like to shorten things up. I always want to make things as simple as possible. And so I'll be referring to this as a definition for what we're going to be looking at today. And that is, it's going to be part over whole. Well, what's the part that we're looking at versus the whole picture that we're going to be looking at, okay? And so if I say that as we move along, understand that I'm referring back to a very general definition of probability. So I know this is kind of a goofy one, but the first example, if a gnat were to land on a ruler, okay? Now this is the key part to this whole problem, right here, okay? The gnat has to land on the ruler. If it doesn't happen, this probability is completely shot because the possibilities are then become a lot bigger, okay? What would the probability that the gnat were to land between the following numbers, okay? So what's the probability in the first one that if the gnat were to land on this whole space right here, that the gnat would land between the 5 and the 6, okay? All right. So if we look there are a total of 12 inches on that ruler, okay? And this span is 1 inch of the 12. And so very simply, the part that he could land on versus all possibilities he could land on would be 1/12, okay? Now you can leave it as the fraction right there. Sometimes people would prefer to write it as a percentage, okay? So if you would prefer that, I'm okay with really either one of those. Just make sure when you calculate that in your calculator, remember we talked the other day, when changing a decimal to percent, you have to move it 2 places. The other day we converted it from percent to decimal, which was moving the decimal 2 places to the left. Now when you put it in your calculator, decimal to percent is the same, but in the opposite, so 2 places to the right. So don't forget that. I'm sure some of you probably have already done the next two already, but if you look at number 9 to 12, what's the probability that the gnat will land in this range right here? Okay, well, you've got, and I'm getting rid of this one now, okay? You've got 12 possibilities, and 9 to 12, you've got 1, 2, 3 of those 12 possibilities present. And so as a result, 3/12 would be what I'm looking for. Now, if you're going to leave it as a fraction, I want it always reduced. So I'm going to divide by 3. You end up with 1/4, which is 25%. Okay? So again, if the gnat were to land on the ruler, that's the key. What's the chances he would land between the 9 and the 12? There's a 25% chance he could land between the 9 and 12. Okay? The last one, what's the probability that if the gnat were to land on the ruler, he would land between the 0 and the 12? Well, if you notice here, That's all 12 inches out of the 12, which, if I reduce that, is 1, which in turn, 100% of the time, if he's going to land on the ruler, he's going to land between 0 and 12. Okay, and I hope that makes sense to everybody. All right, so that's a pretty simple one. You can see it, you can measure it. That's pretty easy. This next one might be a little bit more vague, but again, we're going to try to make it into a measurable problem. So if we take a look down here at this next problem, it says a stoplight at an intersection stays red for 60 seconds, changes to green for 45 seconds, and then turns yellow for 15 seconds. Okay, it sounds like a lot of our lights around here. I know, I think the one out here by the school, it transitions based on weight. Okay, and so if you pull up and you're sitting there and it changes on you, it's because they want to keep the traffic on 12 flowing. And so once you pull up from County Road 9, it does transition. It's got some sort of sensor down there. But there are some lights. My buddy lives in Pandora, and he's got it measured down. The one on 12 in Pandora, it does not have a sensor. It is just consistently, kind of like what this problem is saying, 60 seconds red, 45 seconds green, and then yellow for 15. And so some lights are like this. So if a person arrives at the intersection at a random time, what's the probability that the following will occur? Okay, so we don't have a picture right now of what's transpiring, and it wants you to draw a geometric model. Okay, so what we're going to do here is we're going to draw a picture of this transition from light to light to light. Well, how do you do that with time? Well, I'm going to make a segment up here on the board that's going to represent 60 seconds of the red. So if I go ahead and do that, let's say I make this. Let's say that I'm just making a general, I don't know what happened there. Hopefully it doesn't happen again, okay? I'm just going to make a general length of a segment, 60 seconds red. So, and then I'm going to go ahead and show that 60 seconds red. Okay, now from there it transitions to green for 45 seconds. Now I don't want to make my segment as long as this one because then that wouldn't be an accurate model. So I'm going to break this up into threes. I'm going to make it about that long. Okay, so 2/3 of that length will be 45 seconds. Okay, so hopefully that looks somewhat close to the 45 seconds. Green's probably hard to read. Hopefully not on your computer screen. Okay, and then the last one would be 15 seconds of yellow. Ooh, that's going to be really hard to read. We're not going to go yellow with I'll go orange. Okay, and so 15 seconds would be 1/3 of that. So we're looking at something like this. 15 seconds yellow. Okay, now I've got a geometric model. The segment lengths are approximated to their time length within this transition from red to green to yellow. And now I hopefully can answer the next 3 problems here. So in letter B it says, what's the probability that this person will enter the intersection when the light is green? Okay, well, what's the part over the hole? How long is the light going to stay green? Well, we know it's going to stay green for 45 seconds. Okay. Well, what's the hole? Well, the hole is the transition from the beginning to the very end. And so if you count that out, I have 60 seconds here and 45 and 15, another 60 seconds there. That's 2 minutes or 120 seconds. Okay? And again, if you're going to express it as a fraction, I'm going to reduce that ratio right there. Remember in your calculator, especially the smaller ones, we've talked about using the ABC button to reduce the fractions. You can do that. The bigger ones, don't forget about your math button there. Becomes 3/8. And what is that as a percent? If you did it out in your calculator, 37.5% of the time. So not quite. Well, actually a little more than 1/3 of the time that you enter that intersection, it's going to be green. Okay, so a little more than 1/3. Next one, what's the probability that the person will enter the intersection when the light is yellow? Well, I'm sure that by just doing that last problem, hopefully you got this next one. What's the part? The part is the part that would be yellow, so 15 seconds out of the whole, 120. Okay, and so if I go ahead and reduce that, I end up with 1/8, which is approximately 12.5% of the time. So a little more than 1 in 10 chances, okay? A little more than 10% of the time, we're going to end up entering that intersection when it's going to be yellow, okay? Now for the last one, this is where it gets a little bit tricky. So you have to be able to read problem dealing with probability precisely, okay? The wording can be kind of technical. So in the last one it says, what's the probability that the person will have to wait at the red light for at least 20 seconds, okay? So if I arrive, let's say right here at the red light, okay? I'm not having to wait very long until it transitions to green, okay? So I'm gonna draw up here, if this is 20 seconds, let's see here. I said that wrong earlier. This is actually 3/4 of this one. I said 2/3 for some reason. I apologize about that. Okay, so if this is 20 seconds, which would be a third, I'll try to break that up into a third right here. This is 20 seconds. Okay, and so what I want you to think right now here, I'm going to read the question one more time, and I want you to ask yourself, am I going to arrive somewhere in this zone right here or outside of this zone over here? Okay, so let me read it again. What's the probability that the person will have to wait at the red light for at least 20 seconds? Okay, so if I arrive, let's say right here, I'm probably waiting something like 18 seconds before the light transitions. That doesn't fit the question. The question says at least 20 seconds. So I have to arrive somewhere in this zone over here, okay, between here where it begins to right here. Well, what is that part of that red light? Well, that is 40 seconds, okay? 20 from 60 gives me 40. And we're still doing the part of the whole. So the whole is still 120 seconds. So if I go ahead and take 40 of 120 and reduce that ratio, okay, there's a 1 in 3 chances that I'm going to have to wait at least 40 seconds at that light, okay? And if you want to put that into a percentage, 33 and 1/3% or 0.3 repeating, okay? But again, the important thing I want to stress to you in this problem, two things actually. How do you draw a geometric model, okay? That's how you're going to do it. Time, you can't visibly see time, but we can draw it in a way that we can visibly see it, okay? The second thing is make sure that you pay attention here in D, pay attention to the wording of the question, okay? Because that does come into play. All right, I hope you're doing good. I hope this is making sense. Let's go to the back side now of your worksheet there. If you look at the back side, all right. Looking at the back side, here's what it says. What would the theoretical probability be of hitting the following parts of the target if the dart were to land somewhere on the dartboard? Okay. And so, let me scroll down just a little bit more. So I got all 3 regions that we're going to be looking at here, okay? I really like this problem, and you'll probably see something similar to it on your test next week, so make sure you pay attention here. But the question, the dartboard, let me clarify here, includes this part out here, okay? So you have your scoring tiles, okay? And then you have somewhere outside of that, okay? Still on the board, but probably not scoring anything. And so as I look at this, if I go ahead and talk about the parts, in this situation we're looking at the X region, which would be somewhere inside the bullseye right here. Okay, what's the probability if I throw a dart, it's going to lie within the X region versus the entire dartboard, which would be the outside. So how do we calculate that? Well, in the first two examples I showed you, we were talking about length. It was somewhere on the ruler. It was some part of time, but it was a part of a length of a segment. And so this part, it's completely area. So you got to know your area formula. So the area of a circle for the bullseye is going to be this, pi radius squared over the area of the whole structure, which is going to be 24 times 24, or 24 squared. Okay? Now, in terms of pi, I mean, I can work this out. 16 pi over 576, okay? And if I reduce that down, the 16 and 576, again, you can use those tools we talked about earlier, you're going to get pi over 36, okay? So as a fraction, in terms of pi, that would be your answer. But that doesn't mean a whole lot. I want to know the chances of hitting that bullseye. And if you work that out, we're looking at approximately 8.7%. Okay, which is what you would expect from a bullseye. Okay, there's an 8.7% chance of hitting that bullseye there. Okay, not real great, so you should feel safe, right? The Y region. These next two. Hopefully, you see how to calculate the area. For this next one, the question is, how do I calculate the area of that? That's going to be my part. Okay. Well, what we're going to do is we're going to take the area of this whole circle right here. Okay, and we're going to subtract out the area of what's inside. Okay, if I subtract this portion out, the blue portion from the big red circle, I should have what's left over, that little donut on the outside. So if we do that, the area of the red circle has a radius of 6. Pi times 6 squared. And we're going to subtract out the area of the inner circle, which would be pi times 4 squared. And we're going to put that over this 24 squared, okay, the area of the entire dartboard. Okay. So if I work this out, 36 pi minus 16 pi gives me 20 pi over 576. And if I reduce that fraction, you have 5 pi over 144. So in terms of pi, that would be the probability. But again, that doesn't tell me a whole lot. If I convert this, you get approximately 10.9%. Okay, 10.9%. Well, basically 19.6%. So we're basically talking 1 in 5 chances. If I throw the dart, theoretically, I should hit somewhere within the bullseye and this next ring right here. 1 in 5 chances. Now, some of you may be thinking to yourself, well, it's kind of hard to believe that this chance here is bigger than this chance here, but you got to imagine all that area, obviously we calculated, is greater than the area that we had previously. And so, that's how it falls into play. Now, again, the picture might not be drawn completely to scale, so should probably keep that in mind. Okay, moving on, the very last part, region Z. I get students all the time that mess this problem up. They look at the first one, yeah, that makes sense. They look at the second one, yeah, that makes sense. And then they try to do this last one on their own, and they bomb it, okay? And so here's what I want you to see. I've got this area I'm trying to figure out, this portion right here, okay? And here's what students do every time. They look at the previous problem for Y, and they think to themselves, okay, I'm going to find the area of Z, which would be pi times 8 squared. And then I'm going to take the area of Y, and then the area of X. Okay, now I hope that you got some alarms going off in your head and you're thinking, uh-oh, that's not right. Okay, well, what's not right about that? Well, the deal is this. If I go ahead and subtract out the area of y, the area of y is not that donut-shaped region right there, okay? The area of y includes x. So as a result, when I subtract y from z, the area of y, which includes that inner circle, okay, I'm subtracting x as well. And so I don't need to subtract x again because that's doing it twice, all right? So we don't want that. We just want to take the area of z and subtract out the area of y, which includes the inner circle of x. And then put that over, let's see here, the 24 squared, okay, the area of the whole. Okay, so if I take 64 pi minus 36 pi, I get 28 pi over 576, which, you know, comes as a percent, actually turn that into terms of pi as a fraction, 7 pi over 144, which comes down to 15.3%. Okay, so let's consider that regions X, Y, and Z are your scoring regions. All right, so basically if I was to throw a dart at that dartboard, adding up those percentages there, that's only around 35% approximately. And so I'm looking at a 1 in 3 chances of scoring even a point because there's a greater chance, almost 2/3 chance it's not even going to hit that dartboard. Okay. So I hope that all of that made sense to you. I do have a homework I'd like you to work on for tomorrow on the flip side. Not on the flip side, I'm sorry, on my calendar. So if you could do that for me, that would be awesome, and I'll look forward to seeing you guys tomorrow. Have a good day.